Hello, and welcome to Settle the Stars. Episode 22, Earth, the Pale Blue Dot. Hey folks, this is Alexander Winn. So far in this series, we've explored farther and farther away from home with each episode, stretching our imaginations and expanding our horizon as we proceeded deeper into the emptiness of space. This week, we're returning home to take a closer look at our own homeworld with a renewed perspective. Having traveled to some of the strangest and most extreme environments conceivable, we may find that we see Earth a little bit differently. From out here in space, the most prominent feature is the diversity of environments, clear even from this distance. There is no planet-wide sulfuric acid smog, no vast plains of tectonic scars, no tomb of ice gripping the globe from pole to pole. Instead, through the thin, clear atmosphere, we see hints of a wide range of dynamic systems. Arid deserts, frigid ice caps, rugged mountains, and drenched tropics with mighty rivers. Great continents march through the sunlight under complex systems of weather, all within the embrace of a massive blue ocean. Compared to many of the worlds that we visited, there is no doubt about it. Earth is very much alive. The broad swaths of green foliage visible from space reveal the richest and rarest feature of our planet, the ability to support organic life. But even more than that, the planet itself lives in a geological sense, refreshing its surface over time through continual cycling of the crust along its volatile continental boundaries, and alive in an atmospheric sense as well, with dramatic changes of the weather during seasons and a progression of mighty ice ages and thaws. The oceans are host to most of this activity, and likely the first distinguishing feature that an extraterrestrial explorer would notice. Accounting for an almost insignificant portion of the planet's total mass, 0.023% if you're curious, the oceans dominate the face of our planet, giving it a distinct blue color from afar. That characteristic blue hue is determined by a number of factors, primary among them that the molecules of water preferentially absorb red light and scatter blue light. Because of that, more blue light is reflected back to us, and in deeper water, less and less red light reaches the depths, and the blue light is scattered around more and more. The result is that the more water is present, the more we perceive that blue color. First-time scuba divers will often notice that things seem to change color as you descend, as there's simply less and less red light to go around. Other substances can affect the colors in other ways, from plankton and algae to sediment and organic matter, leading to a range of possible ocean colors you might observe depending on different conditions. Filled with an estimated 332 million cubic miles of water, our oceans cover 71% of the planet's surface to an average depth of about 12,000 feet. But it goes much farther down than that. The deepest part of the ocean is the Mariana Trench in the Pacific Ocean, boasting a maximum depth estimated at 36,037 feet, or a bit more than the height of the cruising altitude for a passenger jet. So the next time you're looking out the window of an airplane, just imagine all the space between you and the ground being filled with water, for a good illustration. The depth of the Mariana Trench is still an estimate because it's not fully explored. Most mapping is done by radar by boats on the surface, because getting down to physically explore is so difficult to do. At the bottom of the trench, all the water above exerts 1,071 times the atmospheric pressure experienced at sea level, and the temperature is just barely above freezing. Not that there's much to see down there anyway. The trench is almost completely absent of life, except for a few varieties of exceptionally rugged organisms and microbes. The difficulties of exploration aren't limited just to the deepest areas, however, and despite the critical importance of the oceans for our economy, over 80% of global trade by volume is shipped by sea, there's still a lot to learn about this part of the world. The use of sensitive geological satellites has aided the effort in more recent years, but even with their help, only about 20% of the world's oceans have been mapped or explored in detail. What we do know is that the oceans are home to some of the most impressive and diverse geography on the planet. The mid-ocean ridges, for example, comprise the longest continuous chains of mountains in the world, spanning over 40,000 miles. That's over 4 times as long as the Alpine Himalayan orogenic belt, which is an array of mountain ranges stretching from Western Europe across Asia to the Himalayas. There are also sprawling basins, great plains, volcanoes, reefs, and canyons, each home to a unique ecosystem environment across the major temperate zones of the planet. The Hydrosphere, as it's called, includes all of the water on the planet, from the deepest saltwater ocean to the most remote freshwater mountain spring, and even the water in the atmosphere. As you might guess, most of the water on the planet is saltwater, a whopping 97.5%. You might be surprised to learn that of the remaining 2.5% freshwater, almost 70% of that is locked up in the icy poles as snow and ice, leaving only 30% in the form of fresh groundwater under our feet, and a mere 0.3% as lakes and rivers. That's less than 1% of Earth's water being currently both liquid and unsalted. Water everywhere, and not a drop to drink. By contrast, the lands of the globe have been much more extensively explored. It's simply easier for us to do, and we are by nature wandering, curious creatures. The travels and spread of humankind have introduced us to 7 continents, from the frigid and hostile Antarctica to the lush tropical rainforests of South America and the punishing deserts of Australia. The continents as we know them aren't just composed of the great land masses, but the huge tectonic plates they sit atop as well. According to the theory of plate tectonics, the crust of the Earth is divided into these huge sheets, pieced together like jigsaw pieces and riding atop the churning liquid mantle of the planet like rafts on a turbulent pond. As these plates are pushed by the pressure within the mantle, they gain huge amounts of momentum and bump, grind, and twist around and over each other at volatile regions called boundaries or faults. Most of their movements are imperceptibly slow to us on the surface, but every once in a while pressure builds and releases in the form of earthquakes, or the liquid mantle erupts to the surface as a volcano. The Pacific Ring of Fire is a huge chain of active seismic and volcanic activity commonly used to illustrate this. Deeper in the Earth, we distinguish different zones or layers based on their physical and chemical properties. The planet is obviously too large for us to study in person at great depth, so we use other indirect methods at our disposal. One particularly useful method is to study the tremors and shaking caused by earthquakes as they speed around the globe. With sensitive equipment, geologists can actually measure these signals as they pass directly through the interior of the planet, not just around the surface. By studying the differences in the amount of time to reach different points and the strength of the seismic waves as they pass through particular areas of the interior, scientists can estimate the composition and characteristics of the material they're passing through. It's sort of like tapping on a box and listening to the sound that comes out the other side as a way of gauging what's inside. After about a century of study with this method, we've worked out that below the upper crust, or lithosphere, there's a low-viscosity molten layer called the asthenosphere, which gradually becomes more thick and viscous as we descend into the mantle. Between 250 and 410 miles down, we transition into a denser but still liquid lower mantle that continues to a depth of almost 2,000 miles. At this point, we reach the outer core, which transitions into the solid inner core at almost 4,000 miles. The core is over 4 times as dense as the crust and maintains a toasty 10,830 degree Fahrenheit temperature. The core is composed mostly of iron with some nickel, and the intense pressure maintains the high temperature that is continuously provided by the radioactive decay of heavy metal isotopes. The discovery of the core was first conclusively reported by Danish scientist Inge Lehmann in 1936. She used the relatively new practice of differentiating seismic waves as they moved through the interior of the planet to identify the boundary of the crust and the mantle. Later, scientists on the surface tried to replicate conditions found in the core in a laboratory, subjecting an iron-nickel alloy to crushing pressure between 2 diamonds in intense heat. The interesting result has led to the theory that the core is made up of gigantic crystals aligned north to south. Some scientists also theorize that the core actually rotates slightly faster than the rest of the planet, gaining as much as 1 degree on the rest of the planet each year as it spins. Whether it's faster or not, the dynamics of a solid inner body rotating against a more viscous outer layer can generate some pretty interesting results on a planetary scale. There are swirls and eddies that can result in a fluid system that rides or rotates above an underlying frame, which is rotating at a different speed. It's like spinning a bowl of soup, where inertia keeps the soup mostly still as the bowl turns around it, but friction with the bowl causes some movement in the liquid. As you can imagine, on a planetary scale over time, huge currents can form. It's suggested that these currents in the upper core result in the generation of the Earth's magnetic field. Called the geodynamo, the electric currents that generate the magnetic field are powerful for a planet of Earth's size, the largest of the rocky planets in our solar system, and the resulting field stretches from the core out as far as 200 times the planet's radius. Out in space, the magnetosphere is distorted by the pressure of the solar wind, which is a stream of charged particles from the sun pummeling the Earth at 200 to 1,000 kilometers per second. The resulting shape resembles, and more or less functions as, a shield, deflecting most of these charged particles from directly hitting the planet. As these particles slide around the shield and down to the poles where the field emerges from the planet to the north and south, the charged particles interact with the upper atmosphere in brilliant shows of light we know as the aurora borealis. The size and shape of the magnetosphere shifts depending on the strength of the solar wind buffeting it. Solar storms, called geomagnetic storms, sparked by mass ejections from the sun, can cause increased torrents of charged particles that can really push hard into the magnetosphere. Some of our listeners may remember the Halloween geomagnetic storm in 2003 that caused a visible aurora as far south as Texas and damaged more than a third of NASA's satellites. Without the magnetosphere, Earth wouldn't be anything like it is today. We're able to witness the effect of the solar wind on other planets and moons that don't have the benefit of such a shield. Over time, the charged particles collide with the atmosphere and cause the molecules in the air, or the air itself, to get swept away into space. On a planet-wide scale, the result is that eventually the lighter gas molecules are blown away into space, followed by the heavier liquid and ice water, eventually leaving the leftover barren terrain. Even some of the hardiest microbes that we're aware of, capable of surviving even with minuscule air and water, would have a tough time on such a world. The complex molecules necessary for life, from DNA to proteins, would be shredded into ribbons in the presence of solar radiation, making the only likely place for survival underground or anywhere away from direct sunlight, which is why scientists are so keen on searching exactly these kind of places on other planets as we hunt for life elsewhere in the universe. Of course, the magnetosphere doesn't protect us completely from all kinds of radiation, that's why we still have to apply sunscreen, but it does allow life to thrive out in the open air enough that much of life on the planet relies on a small amount of solar radiation for basic biological functions. And while it may seem to us like the open air is an endless blue sky, our little bubble of an atmosphere is a small and fickle thing. Overall, the atmosphere is composed of 78% nitrogen, 21% oxygen, 1% argon, and trace amounts of carbon dioxide and other molecules. In the throes of a muggy summer, the humidity can climb quite high in some regions, but globally, the water vapor content only averages about 1% at sea level. The lower atmosphere, called the troposphere, only extends about 6 miles up at the poles, but bows out to about 11 miles high at the equator. The troposphere is the only layer suitable for plant and animal life, transitioning to the stratosphere about 7.5 miles up. This is where most of the activity takes place. It's where we live, where most airplanes fly, and where most of the weather occurs. The complex and sensitive yet deceptively stable weather systems are driven in large part by another Coriolis effect similar to that found inside the planet, whereby the friction of the rotating Earth agitates the atmosphere and generates energy for the weather. Regions of variable conditions, from temperature to ocean salinity to humidity and pressure, all contribute to a tendency for the atmosphere to adjust itself in order to normalize or equalize these differences. It's these adjustments that we recognize as weather. from wind and rain to fog and blizzards. On large scales, the atmospheric phenomena can follow patterns due to regular cycles of variable conditions. For example, uneven solar warming over the course of the seasons, or even just between day and night. Over time, large, stable weather systems can form, like the great meandering jet streams that push weather across North America from west to east, and why a flight from New York to London will take you about 7 hours, while the trip from London back to New York lasts 8. The jet streams arc near the upper boundary of the troposphere, just against the tropopause, which separates it from the higher stratosphere. The stratosphere contains the ozone layer and presents the maximum limit of jet-powered aircraft, stretching to an altitude of about 30 miles. The stratosphere is generally much warmer than the upper tropopause, usually right around freezing. That's because much of the sun's UV radiation is absorbed by the ozone layer, which warms it up. Because of the relatively even temperature, there tends to be very little weather activity in the stratosphere, a trend which continues even higher as the atmosphere gets thinner and thinner. Above the 30-mile high transition begins the mesosphere, much thinner, and as a result much colder, than the stratosphere. Up here, only rocket-powered vehicles can wander, and the highest clouds in the atmosphere can form, polar mesospheric noctilucent clouds. These clouds are rare because the moisture in the mesosphere is so low. The sun's radiation easily breaks apart water molecules this high up, meaning the air here contains about 1/100 millionth of the moisture levels of the air in the Sahara Desert. The clouds are formed from microscopic ice crystals that form in the summer months when this layer of the atmosphere is at its coldest, around -184 degrees Fahrenheit. They can only be seen during twilight, illuminated against the sky as a ghostly white mist. Even higher than the mesosphere lies the Thermosphere, which begins at about 50 miles above the surface. In contrast to the frigid mesosphere, temperatures in the Thermosphere can reach as high as 2,700 degrees Fahrenheit, although the air molecules are so sparse that temperature readings as we know them don't mean much. Temperature is effectively a measure of energy, which we feel as heat on our skin because the higher energy molecules collide more with our skin's heat sensors and make us feel warm. But in the Thermosphere, the air is so rarefied that a single molecule of oxygen travels on average a full kilometer before it ever collides with another molecule. So while a temperature reading would technically be very high as the individual molecules have a lot of energy, there are so few molecules present that your skin wouldn't feel warm at all. Essentially zero water exists at this layer, meaning no clouds ever form. But this is where charged solar particles meet the atmosphere and dazzle us with the aurora. Most people would recognize this region as space. In fact, this is where the International Space Station orbits, along with many of the artificial satellites we've launched. But from a planetary science perspective, it's still a part of the atmosphere. And we're not even done yet. The outermost boundary of the atmosphere is the Exopause, the upper limit and gateway to open space, stretching almost 6,200 miles out. A few molecules of hydrogen and helium float out around here, colliding with each other every few hundred kilometers or so, and constantly falling away into space. But before we follow them out into the void again, let's head back. We said we'd be sticking close to home today. Back on solid ground, it's easy to appreciate how all of these unique characteristics, the atmosphere, the magnetic field, the life-giving water, all contribute to the fragile and rare ability for the planet to support organic life. Scientists and philosophers have been arguing about what it means to be alive for thousands of years, but at the end of the day, it's one of those things that people say they'll know it when they see it. And on Earth, it's easy to see. Life has spread to every corner of the world, from the luscious, most hospitable climates to the most extremely hostile environments. The ancient Greek philosopher Aristotle claims the first attempt to classify the astonishingly diverse forms of life on the planet, and in the 1740s, the Swedish biologist Carl Linnaeus ambitiously set out the classification system we still use today, with each organism belonging to a series of progressively specific designations, from domain all the way down to genus and species. His system of binomial nomenclature is recognizable to us all today as the dual names for genus and species we use to describe everything from dogs, Canis familiaris, to wild Japanese alpine strawberries, Fragaria inumai, and even people, Homo sapiens. Defined by, among other things, the ability to grow and reproduce, and differentiated evolutionarily by the ever-present trudge of various selective pressures over billions of years, life has spiraled out to fill every niche imaginable on our planet. Biomes fitting every habitable climate have grown into complex and many times fragile pyramids of energy transfer, beginning from the lowest productive organisms who get their fuel from the sun, to the larger consumers who eat them, to the predators who eat them, and so on all the way up to the apex predators who sit atop the pyramid until they die and are consumed by those lowly microbes at the start. Despite covering most of Earth's surface, the oceans account for a small fraction of the biomass on the planet, about 1 to 2%, or 5 to 10 billion tons of carbon. And of that, the animal biomass, or zoomass, is almost 30 times as large compared to the plant biomass, or phytomass. Almost all the ocean plant mass is consumed by the animals for energy, so you can see how sensitive the entire system must be to even small changes in the amount of plants. On land, the trend is reversed. About 540 billion tons of carbon make up the total terrestrial biomass, with the overwhelming majority made up of plants, only about 18% of which is consumed by land animals for energy. While obviously not a great indicator of the order of things, the biomass numbers can paint an interesting picture of our world. For example, the single most successful animal species on the planet by biomass today, or perhaps ever, is the Antarctic krill, a tiny speck of a water bug that nonetheless accounts for an estimated 500 million tons of biomass globally, as compared to humans at just 350 million tons. Scientists can also compare the net productivity of an ecosystem by how much biomass is produced, usually by photosynthesis. Tropical rainforests, coral reefs, and algal beds are all close top contenders, each converting an estimated 2 kilograms of carbon dioxide into carbon per square meter per year. But topping the chart at 2.5 kilograms of carbon per square meter per year is swamps and marshes. Whichever way you slice it, the Earth is an astonishingly complex place that we have only just begun to understand. As we learned in our previous episode on exoplanets, the unique blend of features that make Earth habitable and so favorable to life are a rarity, and only foster more curiosity as we search for other possible life-filled worlds elsewhere. The American physicist Carl Sagan wrote a small essay as he reflected upon one of the last images of Earth that the Voyager spacecraft snapped as it sped away into space. The image shows our planet as standing alone against the blackness of open space, like a tiny blue star. He closes his essay called Pale Blue Dot with this thought, quote, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known." I hope you've enjoyed this episode and this series as we've toured the solar system and beyond. We're going to go on a break for a bit, partially to prepare for the future of the show, and partially because I've been recording it while also caring for my 3-month-old twin girls, and as the young folks like to say, I literally can't even anymore. But if you're enjoying the show and you want more soon, be sure to leave a review and tell your friends about Settle the Stars. Every review really helps for an indie show like ours. In the meantime, be sure to subscribe if you haven't already. Settle the Stars is available on pretty much every podcasting platform, and we're also mirroring our episodes on YouTube at youtube.com/edgeworksentertainment. And be sure to ring that bell so you know when there's a new episode. We also have a Patreon page at patreon.com/edgeworksentertainment, where you can get early episodes and tons of other great rewards. The support of listeners like you is what makes this show possible, and I'm so grateful to the people who have already joined. Thank you all for listening. I hope to see you again soon. And as always, this is Alexander Winn from Edgeworks Entertainment saying, happy terraforming. Settle the Stars is a proud member of the Edgeworks Nebula, a collection of intriguing and informative podcasts from Edgeworks Entertainment.
Hedgebrooks Nebula.